Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic, circuit fabrication influences impacting PCB insertion loss. Here's your host, John Coonrod.
Hello and welcome to Coonrod's Corner. My name is John Coonrod. I am a market development engineer with Rogers Corporation Advanced Circuit Materials. I'm going to spend the next few minutes talking about printed circuit board fabrication and how the fabrication can affect insertion loss of microwave printed circuit boards. To begin with, there's a lot of influences in making a printed circuit board that can affect the insertion loss of the microwave or millimeter wave printed circuit boards. Some of these influences are sometimes expected and understood, and some of them are sometimes unexpected. Usually the unexpected influences are those that have to do with tolerances in the process of the circuit fabrication, or it could be some unusual processes in making the circuit, and also it could be even rework processes that are uncommon but sometimes need to be done. Conductor loss is really important because so many things happen in the printed circuit board fabrication that can affect conductor loss. Conductor loss is a component of insertion loss. Conductors that are used in the printed circuit board industry are typically copper, and that's because copper is the highest for conductivity. Copper is extremely high for conductivity, and any metal that's used in the printed circuit board industry is typically lower in conductivity, and that will actually hurt the insertion loss by affecting the conductor loss. Now, one of the more common plating finishes in the printed circuit board industry is ENIG, and that stands for Electrous Nickel Immersion Gold. And that ENIG is a very good plating finish. However, it does have more conductor losses due to the nickel being less conductive. The nickel is about 1/3 the conductivity of copper, and because of that, it actually makes more conductor losses, and the insertion loss of the circuit actually drops some. Okay, this slide is showing drawings of microstrip transmission lines for the first two drawings that are in the middle of the screen. And the top one is what is most often seen for software that's doing modeling for microstrip transmission lines, where the two copper layers are the yellow layers, and they are rectangular in shape. However, in reality, when printed circuit boards are made, they are typically not rectangular. They're actually trapezoidal, and that can be seen in the drawing below that, where it says the microstrip circuit with trapezoidal shaped conductors. That's actually much more real life. And as an example, to the left of that is a microsection of an actual circuit that was taken of the signal conductor on the left-hand side. And you can see the left-hand side of that signal conductor is obviously not perpendicular. It's somewhat trapezoidal, or even has an arc to it somewhat. And also on there I've noted the ENIG plating, and the ENIG plating here is really showing mostly nickel. The nickel is extremely thick compared to the gold. The gold is so thin you can't even see it. But sometimes it's asked, how does ENIG affect losses when most of the fields are between the signal conductor, which would be the bottom part of this copper, and then below that is the ground plane. Most of the fields are between the signal conductor and the ground plane. So why is ENIG actually causing any kind of loss? And the answer really is the conductor has a high current density at the corner, and that high current density is going to be using that ENIG plating. And the nickel, being less conductive, is going to cause more conductor losses. There's another structure that's a double copper layer circuit, which is a conductor back coplanar waveguide, abbreviated as CBCPW. And this is another common structure used in the microwave industry. And this is actually more sensitive to the trapezoidal effects and to the ENIG as well. The trapezoidal effects in this case have an effect on the impedance as well as the loss. So you can see that the signal conductor in the center on this structure has fringing effects, or will have fringing fields, to the neighboring ground conductor to the left and the neighboring ground conductor to the right. Now when that trapezoidal edge changes shape, what happens is the fields actually change to go along with that. And if it's very rectangular as compared to very trapezoidal, that changes how many fields are coupled between there. And because of that, that changes the impedance as well as the loss. So the difference in trapezoidal shape, which does vary from circuit to circuit due to normal fabrication of the circuit, that will impact the insertion loss as well as the impedance. And then also when the ENIG is applied to this structure, the ENIG now is applied to the sidewalls and the top of the conductors. So now again we have fields going between the left signal and the adjacent ground to the left of that. Now you're going through, the electric fields are going through two layers of ENIG, and to the right of the signal and the right ground the same thing. So the electric fields are actually going through more layers of the ENIG, causing more conductor losses with this structure. Now the following slide is going to give a demonstration of some of the concerns with the impedance as well as the loss for these structures. And you can see that the bare copper is the blue curve, And the silver copper, or the silver plating, is actually immersion silver that's plated over the copper. You can see that the silver is laid right on top of the bare copper for insertion loss. There's very little difference with silver and bare copper because silver is so conductive. Now, if you use the same circuit and you put solder mask over it, that solder mask actually does cause more losses, and it's actually causing dielectric losses. And that solder mask, you can see, does cause more insertion loss as shown on the graph. And then finally, the same bare copper circuit with ENIG applied to it, the electrous nickel immersion gold, you can see that that does increase the losses as well. And again, that loss is really related to increasing the conductor losses, mostly due to the nickel. Now the charts on the right-hand side are of a thinner material using 8mm 4003, and the top graph compared to the bottom graph is really a microstrip transmission line compared to a coplanar transmission line. Now on the top graph with the microstrip transmission line is showing a comparison between the microstrip circuit with bare copper as opposed to the ENIG plating, and how much loss difference you get between bare copper and ENIG. And then with the same material, same type of structure, except that it's a coplanar transmission line, the bottom graph actually shows the loss difference between this structure with bare copper as compared to the losses associated with ENIG. That concludes this visit to Coonrod's Corner, and I thank you very much for your attention.
For additional information and technical tools, if you are not already a member, join the Rogers Technology Support Hub and gain access to calculators, technical papers, and more of Coonrod's Corner and other informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.